Hi, I'm Saud Alam, the research lead of the Wayback Machine at the Internet Archive. Introducing TrendMachine, a system to analyze temporal resilience of web pages. It is a product of a collaborative research of the Internet Archive, Old Dominion University, and Protocol Labs. The work is supported in part by Filecoin Foundation. The question, how long does a web page live, is commonly answered with 40 to 100 days, with sources dating back to the late 1990s. The web has since evolved from mostly static pages to dynamically generated pages that heavily rely on client-side scripts and user-contributed content. While it is an interesting question, we argue, is it a useful one? For example, is it fair to call a web page dead that returns a 404 versus one whose domain name no longer resolves? Is a web page alive if it returns content but has drifted away from its original topic? Furthermore, how to assess the lifespan of web pages from the perspective of fixity with the spectrum of content addressable pages to tweets, to home pages of news websites, to weather report pages, to push notifications, to streaming media. Hence, we propose and address a related but different question. How healthy has a web page been throughout its lifetime? As the web archiving discipline matured, many tools, frameworks, and research analyzed the archival landscape in both temporal and spatial dimensions by IIPC members, researchers, and developers at large. These include works that deal with a single archived web page over a short period of time, a collection of web pages over a short duration, a large collection over a long period of time, and a single web page over a long period of time. Our new system, TrendMachine, belongs to this last family of tools. TrendMachine shines when a web page is archived enough number of times for a long enough duration. There are many potential ways to model the changes in the health of a web page over time, but here we will illustrate two of them. Suppose the web page has regularly been returning 200 OK responses for a while, so we consider it healthy. One day, it started returning the 404 not found error. In a linear model, we might choose to say that the health score of the web page has gone down by 10% with each passing day of consecutive 404s. We decrease the health score by 10% until it reaches 0, at which point we call it dead. In an alternate model, we may consider the first 404 observation as a transient error and decrease the health score only by a small fraction. After the first few days of consecutive 404 observations, our hope of the recovery of the web page diminishes. As a result, we drop the health score incrementally more aggressively until we reach close to the other end, after which the web page asymptotically approaches death. If the web page starts to return to 200 OK again later, the health score will go up using a similar trend. This latter model is called S-curve, and it aligns better with our intuition and experience. To model the resilience of a web page, we choose sigmoid function from the family of S-curves, but other functions like tanh are equally as valid. We place 3 parameters in the basic sigmoid function to control the shape of the curve. The spread parameter controls how far up or down the value can go from its starting position. Shift parameter controls how soon any significant changes in the value can begin. Slope parameter controls how quickly the value reaches close to the maximum change. The TrendMachine portal allows customization of all 3 sigmoid parameters, shift, slope, and spread for various HTTP status code classes. A change in any of these values immediately reflects in the corresponding curve previews. We set the shift value of 2xx status code lower than 4xx and 5xx so that the recovery begins quicker than decay. We set spread to 3xx. We set spread of 3xx to -0.5, so the resilience does not go down more than half of its current value, as redirects indicate that the resource might have moved but is still alive. Moreover, it allows configuration for the days of no observations. We argue that the lack of interest of web archives in capturing a web page regularly decreases the resilience of the web page, which is otherwise healthy, as there will not be enough archival records to assess any content changes later. Henceforth, we will use the term resilience instead of health. We set sigmoid parameters of the unobserved class in a way that it does not begin any significant changes for a long while, decreases the score significantly slowly, and does not go too far down. Composite effect of all these curves yields the time series value of resilience. The TrendMachine portal accepts a URL as an input, optional gap filling threshold and policy configurations, and sliders for sigmoid parameters we just described. Upon loading corresponding CDX records, the portal reports various data points and key scores. In this example, we use the homepage of Wikipedia, which has about 3,000 captures in the Wayback Machine with about 40% 200 OK responses. The first capture was recorded almost 28 years ago, and there have been almost 3,000 days with no archival records, of which about 1,000 were filled with likely status codes. The portal reports current resilience, fixity, and chaos scores, along with their recent changes, which we'll talk about soon. The code of the TrendMachine is open sourced, and a demo instance is deployed for exploration. The TrendMachine portal shows the temporal distribution of archiving activities. We notice that the Wayback Machine has been archiving the homepage of Wikipedia more frequently in the recent years than before. We also notice an increased number of 3xx captures in recent years, which are likely a result of HTTPS adoption. In the box plot, we observe that the page is archived as few as 1 or 0 times and as many as tens of thousands of times in a single day. This means sampling data at different temporal resolutions does not scale linearly with their temporal ratios, as shown in the bar plot in the bottom right corner. Due to the non-uniform distribution of archival activity over time, incorporating all the observations in the resilience calculation will cause biases. To address this issue, we select one specimen observation from each day. Our specimen selection algorithm prioritizes various status code classes differently. We first check to see if any 2xx observation is present in a given day. We select the first among those. Otherwise, we repeat the process for 4xx, 5xx, and 3xx respectively until a specimen is found. The lowest priority of the 3xx class ensures that the terminal response observations gets precedence in becoming the specimen for the day, eliminating any non-canonical observations. A 3xx specimen usually suggests that the target location of the redirect is not especially co-located in the CDX response and points to a different URL. Suppose an archive has been observing a web page returning 200 OK responses for many consecutive days, but during that period, the archive did not record any observations on a single day. It would not be unreasonable to assume that the web page would have returned a 200 OK response on that day as well. To incorporate this idea in our specimen selection, we introduce a few different gap filling policies to choose from. In the identical policy, we only fill the gap if the status code before and after the gap are the same. In the closest policy, we fill the first half of the gap with the previous status code and the remaining half with the next status code. In the forward and backward policies, we fill the whole gap with the previous and next status codes respectively. Finally, if the gap is larger than a configured threshold, we do not fill it irrespective of the policy. TrendMachine portal shows distribution of various status codes in the CDX and the state of daily specimens. Most of the self-redirecting 3xx are eliminated in daily specimen. About 1/3 of the days since the first observation has no captures, of which some are filled using the selected filling policy when applicable. Resilience is calculated using sigmoid function on status scores of daily specimen with the initial value of 0.5 and normalized between 0 and 1. It shows that after the first few observations, Wayback Machine did not archive the homepage of Wikipedia for several months in 2002. Towards the end of 2002, resilience score went up slowly due to infrequent archiving. In 2003, wikipedia.org started to redirect to en.wikipedia.org. After 2005, the resilience of the Wikipedia homepage has mostly been stable and high. A fixity score tells whether a web page is changing its content over time. Static files will likely have higher value than the dynamic ones. Fixity is calculated using sigmoid function on content digest of daily specimens. Note that content digest reported in CDX can be sensitive to content encoding, resulting in false alarms even when the underlying content remains unchanged. A chaos score tells how repeated or random status codes in a CDX response are for a given URL. Pages with a fixed status code over time will have a chaos value close to 0, while pages with alternating status codes will have a value of 1. Chaos score is calculated using run length encoding inspired technique on all status codes of the CDX data, in which consecutive duplicates are removed in the numerator. An alternate sliding window calculation is performed on the last n observations as the score becomes insensitive to recent changes on large time maps. A high chaos, along with a high resilience, is often an indication of canonical redirects. The TrendMachine shows transitions of status codes in a specimen of consecutive days. Large numbers along the major diagonal indicate status code stability for extended period of time. Large numbers in non-diagonal cells suggest frequent changes in resilience curve. Web pages with high resilience scores for extended periods usually exhibit large numbers in the top left cell. Large number in the 3xx to 3xx cell usually indicates extended periods of redirection to other URLs. For example, URL restructuring, login walls, domain changes, and path domains. The TrendMachine portal shows a side-by-side comparison of first and last captures. The TrendMachine portal also shows the live web page, if present, with HTTP headers. Some pages might prevent from being embedded in an iframe, which will be reflected in the headers. The TrendMachine system has many potential use cases, such as detect points of interest in a large time map, sample mementos from time maps for visual summarization, detect archival sinks like login pages and paywalls, detect poor quality pages like soft404 in path domains, detect potential link rot, optimize crawl jobs by minimizing wasteful downloads and maximizing coverage, archival quality assurance, cluster pages of a large archival collection in different categories. In the future, we would like to report heuristics-based archival summary by combining various scores, embed captures that can be points of interest, calculate fixity using less sensitive digests, such as SIMHASH, calculate chaos after applying convolutions to smooth out alternate changes, allow alternate web page health models, not just sigmoid functions, deploy in production by integrating with Wayback Machine. Finally, to summarize, we introduce a mathematical model to quantify temporal health of a web page. We built an interactive portal with configuration options for experiments. We described various TrendMachine reports like resilience, fixity, and chaos. We released an evolving open source codebase and provided a demo deployment. You may explore the demo at trendmachine.saud-dev.us.archive.org, and we will see you in the QA session. Thank you.